Today, I'm going to present our paper, Hierarchical Reinforcement Learning Guided Large-Scale Navigation of a Snake Robot. Yeah, we are from Northeastern University. So, our research goal is to find the proper way to control the snake robot to mimic the snake motion in the wild. So you can find the snake robot is just like a way the snake in natural moves, like wave its body to generate anisotropic friction to propel itself under a rhythmic motion of this body. So the robot we developed for this task is the Crater Observing Bio-Inspired Rolling Articulator, is in short COBRA. It's a consists of 11 perpendicularly placed joint that enabling the robot to perform a lot of various gaits or motions given the body structure. So this control schema we adopted to control the robot is called central pattern generator, which is a dynamic system that generates multi-channel sinusoidal wave to control the robot joint motion. So it's you can find the diagram at the bottom, the CPG model. So by setting a CPG parameter, the model can generate multiple channel of sinusoidal wave that's corresponding to the 11 joint of the robots. So the merit of adopting this model is that you don't have to update the parameters so frequently. So once the parameter set is the model following the same pattern to output a sinusoid wave. The second is when you change the parameter of the CPG, the output will not suffer a sudden change. So it's smoothly transit to the next pattern of the sinusoidal wave. So by assigning different CPG parameters, as the animation shows, the robot can perform very complex motion. So for example, approaching the tree and rotating its body to climb it. So by adopting different parameters, CPG parameters, the snake robot can generate various gaits to adapt to different terrains by either achieving maximum energy efficiency or the velocity efficiency. So for example, helical rolling for climbing behavior or the moving in narrow corridor or sidewinding, so adaptive on the slope or lateral rolling, tumbling with various the gaits to perform locomotion. So the problem we are solving in this paper is the robot aim to navigate in a very complicated the maze layout. So as shown, an example shown here, which is a randomly generated layout, and the robot is starting from an arbitrary starting point, and it should navigate to arbitrary goal. So the problem is that it consists of a lot of like U-turn or corners or narrow corridors. It's hard to model in by conventional control method, or even you are preferring end-to-end reinforcement learning is too hard because it's hard. The maze is large, it's hard to perform domain randomization for reinforcement learning. So therefore, we adopt a hierarchical solution to solve such a challenge which separate high-level planning from low-level control. So we stratify the entire control schema to 4 different hierarchies that enable the snake to navigate in such complex scenario. So at the top level, which we call global path planning, the robot plan a path from the start point to arbitrary goal by with the trajectory and segments such trajectory into multiple waypoints. So the entire problem is simplified as to the next level. We just want the robot to smoothly traverse from one waypoint to the next. So it becomes a local navigation problem. So the robot aims to move itself to the next waypoint and then the next waypoint. And the third level is a gait generation. So we want the robot to move to the next waypoint, and we adopt the CPG module to generate the corresponding gaits to achieve the approaching behavior. And at the bottom is a PID controller on the joint space level to follow the CPG output gate as with the planned gate to do so. So let's first focus on global navigation. Here's an example of the maze layout, and the corresponding map is shown as prior knowledge to the robot. So from any starting point and to arbitrary goal point, the top navigation, you can find the planar trajectory in the maze, and it segments the trajectory with several waypoints. It's a diamond. So the problem is simplified as moving towards the next consecutive waypoint. So which comes to the next level of controlling. We have a robot. On the right side, we have this body structure, which consists of the 11 perpendicularly placed joints. So we group this joint into 2 groups and use 2 separate CPG modules to control the 2 groups of the joint. So there's some controlling, or the controller is a train from reinforcement learning shown as the left. There's an actor taking the robot state and output the CPG parameter to control the 2 CPG models. And the 2 CPG models will output the translate such a CPG parameter to corresponding odd gate and even gates to control the 2 groups of the joint. So the Markov decision process of reinforcement learning is characterized as follows. So for the state space, we include the joint positions, the IMU reading, which there's a IMU monitor on the top of the robot head. And there will be a spatial displacement rotation between the robot frame and the next waypoint frame. So we assume the robot can correctly acquire the knowledge between its body frame and the waypoint frame. This is an oracle knowledge from the simulator, but in reality, you can adopt some technology like SLAM. So for action space, the action controls the parameter of 2 CPG components, including amplitude, frequency, shape, phase shift, and offset. For the reward, we encourage the robot to reach the waypoint as soon as possible, which includes three reward. But the first one is the distance to the goal. The shorter the distance to the goal, the higher the reward. The second reward encourage the approaching velocity towards the goal. And the third one will penalize the gait transition that we don't expect the robot takes a sudden change of the behavior. For example, from fast movement to slower movement, this transition will be penalized. So the robot will not walk, but navigate or move more smoothly. So here's a demonstration of a robot in a confined space from any initial postures to approach any destination in the area. So by this way, the robot learned to navigate to arbitrary next waypoint in its neighborhood. So the entire control loop is shown here. So the first module is the search algorithm. By given occupancy of the grid and the start and end location, we adopt a star algorithm to plan trajectory and the segment to waypoints, which is the waypoints are delivered to the reinforcement learning module that taking robot state and translate to the CPG parameters by and the third level hierarchy is for the CPG model to translate the parameter to the gates that's controlling the two group of the joint. So at the very end, you can find the joints on the robot body using PID controllers to track the planned the gait. Right. So we test the robot by multiple terrains or maze layout with a very complex topology, which are randomly generated. We use this to test the navigation capability. The snake robot is controlled to travel from any start point to any given destination. So, for example, there are a lot of the various motions that are taken adopted by the robots. You can find it's a planned joint trajectory by two groups of the joint with a different amplitude, which generates such a gait that we call the sidewinding motion to move to a direction. This is the output of the CPG model, which the parameter is generated by reinforcement learning actor. And moving from the corridor is a little bit complicated. You can find the corresponding joint output. That two groups of the joint are taking completely different motion patterns. So that varies in frequency, varies in amplitude and offset. So which means the corner term motion is more complicated in joint space. Here shows an example that the robot waving its body to traverse the corner to follow the given trajectory. So already planned. It is because the entire trajectory is pretty long. We just showcasing the case as a robot traveling around the corner to follow a section of it. So by planning a different trajectory, the robot is able to follow that trajectory and navigate to anywhere in this maze. Yeah, that's our solutions. Thank you so much.